welcome back. Our next presentation will be by Mr. Anshul Shingdi. He's a contributor to the Maki Data Visualization Library and the author of its geospatial extension, GeoMaki. Also an author of the Geometry UPS package for 2D geographic geometry processing, and contributor to many other packages in the JuliaEO ecosystem. He's also interested in geospatial problems and how principles from other fields can be applied to solve them.
Okay, mic seems to be working. Sorry. Oh, yeah. All right. So, your projector seems to be not quite working. But all right, so while they're figuring that out, yeah, this is going to be a bit of a meandering talk. I'll introduce some concepts around sort of how we deal with big data, how people access it, how you can make that access more optimal, and some of the problems we face, and then we can sort of go in and explore the ecosystem and look at whatever topics are most interesting to you guys. So, there we go. Right, so I call this talk Going Big with, sorry, give me 1 second and adjust this mic. I call this talk Going Big with I/O because a lot of our problems these days stem from the fact that the data that we're working on does not fit on this. It will not fit on your laptop. You can't download it in a reasonable amount of time. And sometimes if it's on the scale of a petabyte, this data is so large that even processing a small chunk of it is beyond the capabilities of your laptop. So, you might say, all right, this is kind of a solved problem. You spin up a cluster, you launch 100 workers, and you process your data. That's expensive. And it's also painful, right? You have to sign up for this account, do all of this stuff, blah, blah, blah. So a lot of what I'm going to talk about today is sort of how you can use big data to solve small problems. And also big problems, but a lot of my work has focused on small problems. So first, let's talk about this sort of new age data access. Earth observation and climate data is often in the petabytes. The data collected even from a single satellite will no longer fit on a laptop. This is not a new problem. Solutions have been tried before. You break up your data set into multiple files, you tile it up, you create these spatial chunks, maybe you store it on the cloud, or maybe you allow the user access through some special purpose server, like a web content system, which is an OGC format, or something like that. But all of these solutions come with problems. Multi-file data sets mean that the user has to know something about the structure of the data set. If you have, I'll give you an example, Copernicus DEM, right, which probably most people here have used. They tile it into 1 by 1 degree tiles. Each tile is a single file. You have to know the format of, if I want the data around this area, okay, I have to find which tiles it intersects. I have to know, given a tile, what's the file name of that tile? How do I get to it? I have to download this thing. It's not easy, right? Large file storage on the cloud, if you have one single large file, even with HTTP range requests, it's hard to download, it takes time. Your queue might get backed up as there's a lot of people doing it. Breaking up large files is expensive because cloud storage providers charge by the number of objects. So S3, right, which is probably the leading cloud storage service today, every file you put on it is called an object. It's a thing. And the more things that you have, the more that they'll charge you. Of course, if you want your user to be able to get only the data they need, you have to have a lot of things because your data has to be chunked up in relatively small chunks. So this is a problem. Special purpose servers need maintenance and they need support from libraries on the user's end, right? For example, in Julia, we don't have support for all these OGC standards of web feature service and whatnot, except through GDAL, which is again slow. It's not guaranteed. So, to paraphrase a much more meaningful saying, I have a dream. And the dream is that a data set should only be represented by a URL. It doesn't matter the size, it doesn't matter the content. That's all that you really need to know. You just have one URL, you access it, and then everything else is readable from the metadata. Users should be able to care about this, but they shouldn't have to care about this. And I'm not necessarily talking about how you use the data, right? Once you get the data that you need, how you use it is up to you. But the problem is, in fact, getting it to you. So how do we get there? How do we get to this dream? So on the right-hand side, I've got some little demos. You can use zar.jl, and you can open an S3, some zar file on an S3 bucket. You can use rasters and zar datasets, and you can open some zar file on an S3 bucket. I recently wrote a Julia package that reads chunk manifest, which I'll talk about in a bit, so you can do that. There's a Julia package called file paths base, which lets you actually, in conjunction with the S3 library, it'll let you treat paths on AWS S3 as paths on your local computer, so you can read directories and download files very easily. But how do we get there, right? How do we get to this dream? So multi-file datasets can be unified using these. Oh, go ahead.
This is a very stupid question. I've never heard S3.
It's basically what they call object storage. So fundamentally, it's just a web server, right? What it's doing is you can request a key from it. And a key is some string. And it will give, if that key exists in its storage, it will give you back some vector of bytes, which is just the file. And generally, the keys are formatted in the same way as directory paths are formatted on our computers. So
It's cloud storage.
cloud storage.
Oh,
Yeah. Yeah, it's essentially cloud storage, if that makes more sense, yeah. So modern data storage methods like, I'll talk about this sharding, where you concatenate multiple chunks into a single file, make S3 hosting a lot less expensive. As Martin spoke about quite a bit, if you optimize your data for the cloud, conceptually you separate the metadata from the data, right? So the metadata is readable without trawling through the entire file. Simple HTTP and S3 interfaces in most languages mean that we can extend this idea of the local file system to the web. So you just treat I'm sure most people in this room have had very, very bad experiences with FTP servers, right? Oh, I connected, but the connection broke, and this and that and the other, and I had to re-authenticate, right? So HTTP and S3 are more transactional. You don't have to keep an ongoing connection. You don't need a session. You don't need any of that. And the last thing, and probably the most important thing from the user perspective, is that all of these operations need to be asynchronous. What does this mean? Well, when you download something, it takes time to download, right? And so if you're doing this serially, you download one bit of data, you download one bunch of data, you operate on that, then you download the next, you operate on that, then you download the next, you operate on that. The vast, vast, vast majority of your time will go in downloading, and your computer's sitting idle. So instead of that, what you can do is you can request 50 pieces of data at once. They all keep downloading, streaming to your laptop. The moment one finishes downloading, you process that, and you move on. And you keep essentially receiving this data in a queue and then processing it as it goes along. So, and that'll become a bit clearer, I think, when I show this demo. But the next question is optimizing access. So I can have a very large data set. Obviously, I don't want to download the entire thing, right? So at the end of the day, all data is just a vector of bytes. That's all it is. That's how it's represented on your hard drive, on your file system, whatnot. Storing a single 1 terabyte byte vector is generally understood to be a bad idea. So let's not do that. What we can do is we can break it up into these so-called chunks, which are basically rectangles or rectangles in n dimensions, hyperrectangles, and the shape of the chunk dictates the optimal form of access. So, and fundamentally, the idea behind chunking is that you download only the data you need. But what does that actually mean? So let's take a look at this data. Let's say this is some example data set. I just put a picture of the Earth, but it could be anything. Now, if this data set, if this is just one file, if this is just one massive chunk, If I only care about something in Iceland, I have to download the entire thing to then decompress it and look at, and then I get the data, I can subset the data around Iceland. Now, let's say I chunk that into chunks that are, I've essentially done, if this one was 5400 in X, 5400 pixels in X and 2700 pixels in Y, then I've made chunks which are 1800 pixels in, 1080 pixels in X and 540 pixels in Y. So essentially there's 5 chunks per axis, right? And so you can see this is a grid of 5 by 5. Now, if I want something from Iceland, all I have to do is I have to download this small chunk and then subset that. So the amount of data that I'm downloading is substantially lower. Now, this is one chunking pattern, but I can do anything. I can do this, right? If I want to scan across the globe, if I just want, so a lot of rasterization algorithms, for example, polygon rasterization algorithms, they operate on a scanline basis. So you actually do one line across the entire plane, and then in that line you can tell which pixels are within and out, inside the polygon and which pixels are not. So in that case, this is a very optimal chunk pattern because I download this and I run all of my complicated algorithms on this thing. Then I download the next one. I run all of my complicated algorithms on that. So all of the data that I require is made available to me. So, but, right, if I wanted to access just a small chunk around Iceland, then I have to download this entire thing to get to this. So the choice of how you chunk things really, really affects how your user will be able to use your data, how long it will take them. And chunking is, of course, not restricted to 2 dimensions. It's also very interesting for n-dimensional data sets. Let's talk about 3D for a second. Let's say I have a 3-dimensional data set, 2 dimensions x and y, 1 dimension time. Right? It's some time series of, let's say, Earth observations, weather measurements, simulations, whatnot. If the users of your data set are interested in looking at one small region of space, but across all time steps, then you want your chunks to be very, very long in time and very, very small in space. If they're interested in global overviews, right, you want to look at the average temperature of the world or something like that, but at a single time step, then you want to have chunks which are very large spatially, but small in time. So I'll show you, this is a visual example, right? So this z-axis, the upward pointing axis, is time. The x and y axes are x and y. And you can see that these chunks are very, very long in time and very small in x and y. So if I just want data from this chunk across all time, it's very easy. But if I want to get a global overview for one time step, it means I have to download the entire data set. Right? So you can see where these trade-offs sort of start coming into play. Mm-hmm.
And so what is stopping people from making too many chunks?
What is cost? Cost and the fact that, okay, when you download something, right, there's sort of 3 stages to it. One is you send the request, the server processes the request, and then you download the data. So with small chunks, the time taken to download the data will be small, but the time taken to send the request to the server and for the server to process that is a fixed cost, right? That's static. So if you have too many chunks, then the overhead from requesting your data from the server is very high. But if you have too few chunks, then of course you're downloading too much data. So there is a trade-off there that you have to manage based on what you believe your user will do. Go ahead.
So, just to clarify, so we're not actually storing the chunks ahead of time. We're storing the entire image and then we're chunking it somewhere in the back, right?
No. The chunks are stored separately. So actually, you know what? Let me see if I can do this.
It might also be helpful to mention that a chunk is the compressed.
Yes. So the big thing about a chunk is that this thing is a single unit. So if I want to compress that, I just compress this individually, then the next one individually, then the next one individually, and so on and so forth. Right? So what you don't have to worry about in this case is you can decompress them also individually. Because if you compress the entire thing, then you have to download the entire thing to decompress. So go ahead.
How to figure out the best number of chunks like that?
Yeah, so well, let me show you the next slide. And so this is an example of chunks which are very wide in space but very small in time. right? So if I wanted a global overview at some time step, then I would just get 4 chunks instead of all of the chunks of the data set. So the question that you have to answer is, what are your users trying to do? So, and it may very well be that you want to do both, right? So you just put up 2 copies of the data set. One is chunked in space and one is chunked in time. That's also something you can do. Does that answer your question or not really? Cool.
My question is, with chunking, is the quality of the data affected at all?
No, not at all.
You're just cutting it and you're not having an impact?
No. You're essentially chopping the data up into little bit, but there's no loss. The only loss that you could have is if you choose a lossy compression method. So, for example, a PNG is completely lossless, right, in images. But JPEGs, you'll notice that they're smaller, but the quality is a bit lower and stuff like that. So if you choose the wrong compression method, then yes, absolutely. But in general, with the defaults, there will be no loss. So yeah, so as I said, these are just 2 different examples of chunking schemes, right? And so you of course have to choose the one that works for you, that works for your users. But if I look at this again, this is a 10 by 10 grid. This is about 100 chunks total, right? And this is, let's see, it's 10 by 4, so it's about 40 chunks. So the more granular the chunks, the more of them you have. And as I said, that means that on S3 you have a lot of objects, you have a lot of cost. Now, in order to avoid this, very recently in the ecosystem, this idea of sharding has come up, where you concatenate multiple chunks into the same file. So if you are storing one chunk as one file, then you run into these S3 issues, where just because of cost, you have these gigantic numbers of chunks. But if you concatenate chunks into the same file, what you can do is you can essentially, with the HTTP range requests, you can decrease that cost substantially. But the cost that the other complication that you introduce is that, of course, now you have this file with a bunch of chunks, and you have to store the offsets for each of those in bytes and so on. Excuse me. So it introduces a lot of complication, but it can also improve your web caching speed if this is a data set that you're delivering to a lot of people. It can improve download speed if you use it correctly, things like that. So, sorry, someone had a question? No?
I was just going to sharding is what we saw in the previous presentation, right?
Yes, so what Martin was talking about was mostly single file data sets, right? So a single file is, in that context, is a shard. And then if you have, I mean, at NASA and places like that, you have these data sets with millions of files, right? And so each file is a shard. Inside that, they have chunks, which are compression units. So let me give you a more visual example, right? This is the same chunk data set from before, but I've put these little white lines. And so now imagine that each of the large boxes is a single shard, right? That's a single file, within which you have these smaller compression unit chunks. So what you can do here is, of course, each of these small chunks is individually downloadable, right? But this is one object, this is one object, this is one object, this is one object. So now, if each shard has 25 chunks, and there's 25 shards, you have decreased your storage costs by a factor of 25, because you've decreased, at least in the dimension of number of objects. You've decreased the number of objects that you're storing by a factor of 25. Alex, go ahead.
The price per object is a component of the cost.
Right, it's not the whole cost. Yeah.
Saving your storage.
Yeah.
That the storage cost will still be dominant cost.
Yes, they're still quite high, but and it's not just that, right? You can also, if you want to use an older workflow, you can also download the entire shard. If you know that you require the entire shard, you can just download that and then decompress on the fly as well, right? So
So is each one of these considered a shard, or each, I want to say square, but it's all squares. I mean
the bigger ones and the smaller ones. The bigger ones are shards.
Right. And then the individual,
Yeah.
so squares. Those are the
Those are the chunks. Yeah. So I'll show you this graphic, which should probably, I probably should have shown this earlier. But in the context of your data set, right? This is just one array in the data set. You have a shard which holds a bunch of chunks. And so the shard is the unit of storage, and the chunk is the unit of compression, or transformation, or what have you. So in this case, in a lot of situations today, if one shard is one chunk, then this and this are just the same thing. But in the general case of like, I send you an etcdf file, or I send you an HDF5 or a GeoTIFF or whatever, then that file is a single shard, and then that contains these multiple compression units. So this all sounds a bit familiar if you work in geospatial, right? I'm talking about these shards and chunks and whatnot, but really this is just the same multi-file data set model, right? You have one file per some, let's say maybe 1 by 1 degree, maybe something else. You have one file per 1 by 1 degree square. And then inside that file, you have chunks based on whatever your requirements were, right? But the beauty here is that it's concatenated into a single logical data set. So I only have to load one thing, right? From my mind, the only code I'm writing is one line. As opposed to this, if you have actually multiple independent files, then you have to load each file, or if you're using X-ray, you load the multi-file data set, which takes time, and stuff like that. So the user doesn't have to know about it. That's the cool part. So yeah, if each shard is an HDF5 file, or if each 1 by 1 tile is an HDF5 or an etcdf, then each chunk is the chunks of the file. So now I've been talking about this ZAR thing, but what actually is it? So ZAR is an open format for storing large, multidimensional data. It's flexible, extensible, multi-file by default. So the chunks are stored in this like hierarchical directory structure, but the metadata is stored in separate files. It's stored as JSON. So it's human readable, it's not very large, and the nice thing about ZAR is because it's community extendable, chunks can be compressed and transformed in a lot of ways. So it was very difficult, for example, to store variable length strings in binary files. Not all file formats had support for that, but in ZAR, it's easy enough for you as a user to just add that. Or if you have some new compression algorithm that you believe is good for your particular use case, and I think Milan wrote one of those actually, so we have someone here who's done that. This is the bit information thing that they added to numcodecs. But yeah, you can just create a new codec as and when you like. And of course, that doesn't mean that everyone can use it. You have to get it supported by the community. But it's a lot more accessible than it used to be. Where earlier in HDF5, you would have to go through this like arcane approval process and write C code and all of this stuff. So let me just show you quickly the directory structure of ZAR. Can everyone read this? I tried to zoom in as much as I could, but so this is my top level directory. It's called test.zar. Inside here, I have a file called .zgroup, and I have a bunch of folders, but each folder is equivalent to either a group or an actual array. And so a group is just a collection of variables, right? Go ahead.
So test.zar is just one ZAR file.
It's a folder.
It's a folder.
It's a folder that you call test.zar.
So this is a file system.
Yes. No, it's not the actual file. This is a file system, right? So that is one potential drawback of ZAR, right? Is that it has to in size, it's not necessarily larger than HDF5 or what have you in physical, like actual size on disk, but the structure is a bit complicated. So you can zip this up and it'll work. Most ZAR readers can read a ZAR within a zip, but it's just one more thing you have to keep in mind. So ZAR was really meant for cloud storage and that kind of thing. Because if you think about the directory path it takes you to get to this, right? test.zar/ti/0. So the ability to figure out the file that you need is actually very simple. So there's this thing called time, this thing called x, this thing called y, and my actual data set, which I think I left unnamed for some reason. But so you can see that here, for example, these are all vectors, and so these all just have one chunk. And then this unnamed is a three-dimensional array. So its chunk is 0.0.0 because it's chunk 0 in dimension 1, 0 in dimension 2, 0 in dimension 3. So this is kind of chunk indexing. ZAR is not natively dimension aware. So ZAR will not know that this unnamed array connects to this time or this X or this Y vector. But X-array and most ZAR readers these days, they've introduced this key called array dimensions, which I'll show you in a bit, which basically, it's a metadata key which tells you what this is. Very similar to what happens in climate and forecast compatible files like netcdf or things like that. So let's look at, so I'm going to look at this file now, the .zarray file in X. So it tells me that the chunks are of size 100 and there's one dimension. Then it tells me there's no compressor, so I haven't used any compression. This is a Python terminology called dtype, which basically just means data type, right? It is an 8-bit integer, so in64. There's no filling value. There's no filters, which are just arbitrary data transformations. So you can do, for example, scale and offset through a filter. And it gives you the order, which is column first. It gives you the total shape of the data. So in this case, it's 100, so there's only one chunk. If it were, for example, 101, 102, then there would be, or up to 200, there would be 2 chunks, right? And then 300, so 3 chunks, and so on and so forth. And the ZAR version, which is 2. So now ZAR version 3 is kind of out. It's not really widely supported beyond Python. Python is itself pretty big, so it's kind of out. And ZAR version 3 introduces a couple of new concepts, but fundamentally, it's still the same thing. So that was the ZAR-specific metadata. Now we get into this file called, and this is all JSON, right? So this is all JavaScript object notation, super easy to parse, super easy to look at. Now this is Z attributes, which is completely user-defined attributes. And so in here, you'll see that there's this key called array dimensions, which is X, right? And there's this key called axis, which is capital X. So that just means that this is the X-axis of the data. This is more of a climate forecast convention thing. And so if I looked at that unnamed thing down here, right, and I looked at that zaddrs file, this array dimensions would have been X, comma, Y, comma, time. So if that sort of helps make more sense. Yeah, again, just to reiterate, the way a chunk works in ZAR is that this is your entire array. Within that, you have these, let's say you have 4 chunks in that array. So these are addressed by A.B.C, depending on the number of indices, number of dimensions. Now, what happens when you read a chunk is that you'll recall that there were specifications for a compressor and some filters here. And so actually this is what's happening when you write a chunk. So this is raw data, let's say, right? This is your numbers, maybe if it's temperature, it's in the range from 260 to 300 or something, right? These go through filters, so that might be, for example, a scale and offset filter. It might be some form of quantization, some form of delta encoding, stuff like that. So delta encoding is where each value is relative to the one before it, right? So there's a lot of different things you can do here. And then it goes into a compressor, so that can be zip, BLASK, LZMA, lurk, all that stuff. Once it's gone into a compressor, you essentially just have a vector of bytes, and that vector of bytes gets stored as a file. So this is essentially the structure of ZAR, if that makes sense. And it's very similar to what you have in HDF5, right? It's very similar to previous solutions, but it's just a bit more understandable and easier to read. So for example, there's a reader for ZAR in JavaScript, right, which Alex uses on a web page. Now, if you try to tell me that you could upload HDF5 to a web page and have that read automatically, I would be very impressed. Without a server, mind you. No server, no backend, no nothing. This is all running in your browser. So the core ZAR spec is super simple, right? It's just, given some indices of an array, can you convert that to which chunks you need? Given a chunk, can you convert that to data, or can you go the other way around? Given the data, can you compress that into a chunk? And the last question is, of course, given a chunk index, how do I get that chunk physically? And so that could be either, simple file system, could be S3, HTTP, Google Cloud. You could go into a zip file and decompress on the fly and look at that. So that's ZAR. And now, oh no, I seem to have misplaced this. Oh well, I'll find it. So let's talk about Kerchunk. So this is a name that you've probably heard floating around a lot. But what is this thing? Well, we love the ZAR interface. It's really simple, straightforward, can do a lot. But we need to access data that is not stored in ZAR. We need to access all of this data since 1970, right? Which is when satellite imaging started to take off. And that's all stored in, if you're lucky, NetCDF4 or HDF5 or GeoTIFF. If you're not lucky, then it's stored in something else. GRIB, FITS, which is astrophysical images, all these like even more obscure file formats. How can we do this for multiple files, for all of these crazy data sets, without stepping out of the ZAR world? And so the fundamental concept is that a chunk is a chunk, it doesn't matter where you go. Right? Any data format that stores chunks must, by definition, store them as some vector of bytes. And if you give me a vector of bytes and I know what you've done to it, I can probably undo that. So we know that HTTP requests allow you to get specific byte ranges from files. So the concept behind Kerchunk is that you create what's called a chunk manifest that maps logical chunks to physical byte ranges in some random file, arbitrary file. Right? And so this maps chunks, this maps the chunk address 0.1.2 to some range of bytes inside some HDF5 file or some GRIB file or something. So, you go from a chunk address to a file, let's say myfile.nc, and some range of bytes. Maybe you go from byte 1204 to byte 5502. I just made these up, right? This mapping is stored in a JSON file. It's created by going through a data set. And this can be one file, multiple files, anything really. And you open each file in the data set once. You retrieve all the metadata. You compute the position of each chunk in the larger data set, right, in the global data set. And then, once you pass out all this metadata, you store this information in the Kerchunk JSON file. And this allows, theoretically, millions of files to be referenced and accessed from this one single data set. So, I duplicated that. So this is an example of a Kerchunk mapping file, right? So what they've done is each key, this is JSON again, each key, it's kind of like a dictionary, each key here is the name of the file or the path to the file. And the contents can either be a string, which is just the contents of the file, or like this, it can be a path to a file and some byte offset and some byte length. This is an extension to that. So it's, well, what has basically been done by Kerchunk is that they fake your file system. So what you show ZAR is a file system that has all of these keys, right? But when ZAR tries to read this file, Kerchunk, or in this case Python's FSPEC library, which is a part of, it's not part of Kerchunk, but Kerchunk functionality is implemented by FSPEC, right? So FSPEC meaning file system specification. So Python's FSPEC library will go retrieve this byte range from this file and present it to ZAR. So that means that this can be anything. This doesn't just have to be from one file. This can be from file 2.nc, file 3.nc, right? Or tile underscore E60 underscore N25, right? It could be anything. Mm-hmm.
I don't see in this list the indication of what you use to read the file. That sort of, is that sort of assume like this is an NetCDF, right? So you know sort of here what you use in media. You know what I
Yeah, so in terms of software, so this whole ecosystem started out in Python. So in Python, if you pass Xarray a reference to this JSON file, it will understand that. And then, but there's no, okay. So do you mean specifically once you've got the chunk, how do you decompress it? Or how do you interpret that? Or like,
Let's say that these are flat binary or grid or next year or
Mhm.
CSV or whatever, right? But you need to know how to get to the data and expose it from the store.
okay. So you're asking how you create this file,
No,
essentially, no.
I think you are starting to answer it with Xarray. So
Okay.
Xarray
Sure. Yes, okay. So you would tell Xarray that this is a grib file and that's how you open it. So for this, how do you tell it that this is a chunk file and that's how you open it?
yeah, so
Yeah.
Julia
Yeah. So that's what I just did actually a couple of months ago. So Alex and I, we wrote a chunk interpreter for Julia. So it basically does the same thing, a similar thing to what I described in Python's FS spec, is that Julia has a zar.jl, right? And within zar.jl, what we do is, or rather, as an extension, as a package that depends on zar.jl and extends it, what we do is we define a specific zar storage mechanism, which is backed by this JSON file. And so for example, so this zar storage mechanism backed by this JSON file. Then what happens when zar.jl requests a file from our store, from our storage mechanism, chunk.jl looks up where that key is in this list. It finds it. If it's a string, then it just returns the string. If it's a reference, then it downloads the relevant bytes and returns those. So the way that you would actually use this is you would load chunk.jl and zar.jl. And if I go all the way back here, I can write it out later, but essentially using chunk, using zar, if you're using the rasters, you maybe use zar datasets if you have a CF, if you know it's CF compliant, which most chunk datasets are, because they come from CF compliant files in the first place. And then you essentially just start with reference : / wherever your chunk file lives. And that essentially sorts it out. So does that make sense?
Yeah, no, I think so.
Cool. Okay. If it helps, I can just walk through the tests of chunk, and there's a little demo there, which might make it a bit more obvious.
So in that, you can't see actually on your screen there that you're actually forcing rasters to use Açores. That's how it knows.
Yeah. For raster specifically, you have to tell it that it's a zar file.
You have to tell it that it's it doesn't know that string, the rasters detected. So you just say source is Açores.
Right, and then ultimately zar gets the string from
Yes, zar gets this string.
and then interprets that.
Yeah, based on this reference : / zar will know to interpret whatever it sees as a chunk file. Well, if you've loaded chunk. If you haven't, then all bets are off.
So just saying the implication is that at some level of care chunk or zar, there is a list of known formats.
Yes. But I think that's the case for most file I/O libraries these days.
Yeah, that's
Yeah.
fair. I was wondering whether.
Yeah. So, right, so this was the file format. Now, one disadvantage of chunk is that it's completely flat, right? So if I look at this file, this is fine when it's just 3 or 4 files. It's fine when it's 100 files or 1,000 files. When you get to the point where you have 1 million chunks, 2 billion chunks, 1 billion chunks, then you run into problems. Because you have to parse through this entire text file or look through this entire dictionary every single time you want to retrieve a chunk. And there's some ways to accelerate that, but fundamentally, the problem's still kind of the same. So nowadays, there are a couple of new technologies that have come up. So virtualizar is one of them. It's basically just a way to. Virtualizar started as a way to create these chunk manifests in software, right? So what you would do is in Xarray, or if you use dimensional data in Julia, right? In dimensional data is our equivalent. every data set, once you get down to the bottom level, there's some array which backs that data set. There's some matrix in memory or three-dimensional, four-dimensional array in memory. And what virtualizr did was it said, okay, instead of faking out the file system, let's fake the array representation. And the array is what they call a manifest array. And it's changed a bit since then, but I just want to explain sort of how this came about. The array is what they call a manifest array. And when you requested a datum from some index, or when you requested a certain chunk, that manifest array knew where that chunk was located. It went, it located it, it downloaded the data, decompressed, and returned it to Zar. And so this was basically, what you gain with this is a little bit of hierarchical structuring, which this doesn't have, because this is just a list of file names. And now virtualizr is actually built on top of Kachunk. So all the capabilities that Kachunk has, virtualizr has as well. It can emit Kachunk files and things like that. So let me now open the web. And so virtualizr is a GitHub repo, right? If I zoom in a bit, is this readable? Or should I zoom in a bit more? Sweet. So yeah, well, the other thing about Kachunk that I forgot to mention is by nature it's completely cloud optimized, right? Because every potential bit of metadata you could want is in this JSON file, which you just download. So you don't have to prefer the cloud at all unless you're retrieving data. So yeah, virtualizr kind of grew out of Kachunk. This manifest arrays thing is kind of an intermediate layer in memory. And if I look at, this is in Python, of course, but given that you can always call Python from Julia by Python call, this is usable as is pretty much. So the way you do this right now is you would use this concept of a virtual data set, which let me zoom in a bit more. So you would open these virtual data sets, you have all of this bunch of files that you want to make into one data set. So you'd open them with virtualizr, you'd use Xarray to combine them, and then you would dump that out as a Kachunk file. And then you can just use Xarray or kachunk.jl and zar.jl to open this as a Zar array, essentially.
Have you thought about adding this to kachunk.jl? Because Rastus can already do that combining.
Oh,
So we can easily just write that.
so now we didn't have concat disk arrays before. Now that we do, one thing we can do is we can create a virtualizr-like manifest array in Julia, and then, yeah, life becomes a lot simpler.
Like you can just open the folder as a Rastus series, and then you just combine the Rastus series and be a concat disk array.
Yeah. Well, the big thing, so another one.
Code at the top, you just can't say that it's a kachunk.
Yeah. One of the big things that Kachunk did, right, is it actually, a lot of the hard work was figuring out how to get the byte ranges out of these files. And so if that is solved, then there's no reason you couldn't have a Kachunk in Julia. On the flip side, I mean, would you really want a Kachunk in Julia? If it already exists in Python, it seems like it may be useful, but it seems like a lot of effort that could be spent elsewhere right now. So to my perspective, a reader is probably fine. Most people who are Kachunking their data sets will do it in Python anyway. I mean, the potential to convert them to Julia is quite low.
I think the generation of Kachunk is very much provider specific.
Yes.
As opposed to user specific.
Yes. Because, well, I mean, the thing is, right, generally, if you have a 1.4 petabyte data set, it's very, very difficult for me as a user to create a Kachunk of that. But it's very easy for the person who's generating that data set. As you generate it, you just spit out a Kachunk file too. Right? That costs you nothing. So,
Maybe another comment to this.
Mhm.
I think it's very useful to have a package called kachunk.jl, because the same way, the first question I get whenever I try to tell people that we use Python, look at Julia, they ask me, where is my Xarray?
ah,
The next question that comes
Yes.
opposed to something like some data. It's quite useful if I want.
Yeah. No, absolutely. Let me actually. So we do have a kachunk.jl. What happened here? Oh no. Okay, I have to look at that. But yeah, we do have a kachunk.jl. You can just install it. It kind of works out of the box these days. Yeah, I need to update the documentation, but it does exist. And for most kachunks, it'll work okay. There's an ignored part of the kachunk standard that they define, which is basically like generative templates. So you could define a list of variables that kachunk would for loop through and do nested loops and kind of try and generate byte ranges. The problem with that is, of course, that byte ranges are arbitrary, effectively. So there's no way to encode that in a more compact way than listing them all out. So but some files still use that, but that's not really a big thing, I think. There is another package called fspec.jl. Oh, 5 minutes. Oh, I only have 5 minutes. Okay. Let me run through this really quick. So the new hotness is called IceChunk. And this thing is basically building on top of virtualizer and kachunk. And the idea is that what would happen if instead of storing my ZAR chunks in these directories and nested folders and whatnot, I just store them as content address binary blobs, right? Some random hash as a binary blob. And then I have a metadata file that given a chunk address points to that binary blob. The advantage of this is twofold. One, if you have a kachunk data set, you can't write to it, ever. Because the moment you write to it and change the length of that chunk, you've broken the entire kachunk file. Because you've broken the bit ranges, right? They're no longer the same. So with IceChunk, what you can do is, IceChunk supports either you have a single file, which is a chunk, you have multiple chunks in one file, or your chunk is just file, byte, and byte range. And so what you can do is you can start with a kachunk file, and then as you edit this, IceChunk will automatically replace what you have with local chunks, effectively. So, but the big thing with IceChunk is not that, right? The big thing is that it's meant to be a transactional storage engine. What does that mean? Because your chunks are not directly stored, they're referenced, your metadata file can just be a single, you can use like a Git style interface for your metadata file. And so whenever you change a chunk, that's just a change to the metadata file and a new file in the chunks somewhere. But if you store the metadata file before and after you made the change, you can roll back that change back. And that means that you can coordinate changes coming from multiple users or from multiple jobs on your distributed task or whatever, right? Because earlier what used to happen, if you changed the ZAR chunk, you would change the entire chunk and you would have to upload that chunk again, which is still the case here, but the chunk would go to x/1.2.3. And if another user is trying to write to x/1.2.3, you don't know which one worked. So your data is now effectively corrupted, or at least wrong. And with this, one transaction will fail, the other transaction will succeed. And you know which transaction failed. So then you can redo the computation or whatever you have to. And IceChunk actually, they also implemented their own I/O in Rust, so it's, I think, a factor of 2 faster than what they have in Python right now. So that is also an advantage. But the file structure is again a bit more opaque because you have this metadata file and then you have all of these like random content address chunks. So I think it's definitely something that people should look at, but it's a trade-off as to what you need and why you're using it. So yeah, I guess my time's probably up.
I have 1 minute.
1 minute, okay. Any really quick questions? All right.
Actually, there are some sort of difference between NetSDF and ZAR.
Mm-hmm.
For instance, when you have the field value,
Ah, yes.
so in NetSDF it means it's missing, while in ZAR it rather means it's a default value.
Yes.
Parser would
Yeah, 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 yeah.
Apoie value would be 0. But it doesn't mean
Yeah.
it's missing, it's just 0.
Yeah.
And another thing is that you cannot store none in the as a null. As a JSON file, you have to store it as a string.
Mm-hmm.
So you cannot have an attribute which has to value none except for the fill value.
Except for the fill value, yes.
Which is as a special.
Yes, 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 yes.
So did you come across?
So I came across a couple of CF issues, but not that specific one. That being said, yeah, because the CF implementation is so different. Felix, you're saying?
Regarding the difference between fill and missing, there's in Zara still has missing keyword argument to force it to use to replace the fill value as missing value. Because sometimes you want to have that, sometimes you don't.
Would be better if I had a different name. So that would not be ambiguous. What's now?
Well, I think that's a problem with the Zara specification.
Yeah. It's
But that's a distinction in the Zara specification.
yeah.
Use case. Because basically in Zara, if your whole chunk is only is not there, it will fill it up by the fill. That's the point. So that you don't have to write the chunks that are not there as empty files. And then you could use that as missing value. Missing value data, or you can use it as
Right.
Something related to this is also the chunks are not there. Some servers report missing chunks. And
That's a problem.
unfortunately, that's how many servers are configured, and it's not going to change. So even if you have if something's not there,
Right.
you get an error like missing item.
That's awkward. I mean, I imagine that that's probably something that one could look at in Zara.jl itself in the way that it handles HTTP replies, right?
Yeah,
But
Cities already implemented a special case.
okay.
Where you can say, okay, if it's a missing item, I will just
Yeah, 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 yeah. Just assume it's missing.
It's not there, but not the default. So
Oh, sure.
Just a question. Maybe you could now maybe later in the book, do you have examples of actually working with chunk data or ice chunk ideas in Julia?
Yeah, so ice chunk, not yet. It seems doable to do like an interface through Python to Julia for ice chunk, but still have to figure that out. In terms of CoChunk, there are a couple of examples that I have, but the problem is that the data sets keep getting updated, so the files that I have keep breaking.
Yeah, it does seem to be in flux.
Yeah, it's a bit
New ideas.
it's a bit tough, but definitely doable. I can shoot over some notebooks and stuff like that.
So is that a problem for Python as well?
Yes, any consumer of CoChunk will have the same problem if the data set changes.
You actually need getting
Yeah.
chunk files.
Yeah. Well, I mean, you can refer to a CoChunk file on the web. So you don't but you have to download it all the time, but that's not so bad. But yeah, I mean, in terms of minimizing complication, I think IceChunk is the way forward in that sense. Because it's storing everything controlled by the provider, right? So, cool. Well, I think, Martin, you're up. Thank you.
Thank you, Mr. Anschel. Up next, we have our second presentation of the day by Mr. Martin.
Sorry for that. So I'm back. I think when I was asked to present here, I said I could do a second topic, sort of a suggestion. And when I took a look at your program a month or two later, I was actually in there with a second lecture. So I had to prepare something more in the past few days. But I'm happy to do so because geomorphometry is actually quite close to my own research. I don't need to introduce myself again, but this lecture or this talk is mostly related to my research as an external PhD candidate at the University of Delft. So, geomorphometry, what is it, what's relevant to it, and what can you do with it in Julia? And geomorphometry, even though it's maybe a difficult term, you can basically split it into geo, morpho, and metry. So geo implies terrain and earth, morpho is the shape, and metry implies quantitative analysis. So we're really analyzing the shape of the terrain of the earth. So you take an elevation model and you do some analysis on it. So how steep are the mountains of the island of Terceira would be a geomorphometry question. So everything comes back to elevation. And many things, also in my daily job, where I'm a researcher at Açores, we do many things, among which is hydrology and flood modeling. And all of these analyses, your basic input data sets for your numerical models, they start with an elevation data set, right? If it starts raining here, will this area flood? You need an elevation data set to answer that, right? Will those waves that we see with the nice storm out there, would actually reach this hotel? Question of elevation. A picture here of the infamous Bikini Atoll for the atomic tests. But essentially these islands and many atolls in the Pacific, they're threatened by sea level rise. And that's also a question of elevation. These islands are basically 1.2 meters above sea level. And you need to know that very precisely to actually have an idea about when sea level rise is actually very threatening, if sea level rise is millimeters or centimeters. So sea level rise is a big important one. Subsidence is also an elevation component, and subsidence is happening in a lot of coastal cities around the world, and the subsidence signal in terms of elevation can be more than actual sea level rise. Landslide analysis and many other types of analysis you could do in elevation. So for my work, and I'd say for most of my research institute, I think elevation is the most important metric you could almost have. Don't want to play it up too much though. Other important data sets as well. So this is basically your starting point. And I thought I can tell you about geomorphometry and the actual stuff you have to do in Julia, and the many small differences you can have in all these operations. But actually, I think the most important thing is your source data set that provides the elevation, because it has way bigger errors than any of the algorithms you will actually use in these analyses. So I thought I'll spend, I think, 3/4 of this lecture actually discussing global and local elevation data sets. These all have, well, these are famous missions. So in terms of elevation, I'd say there are 3 major sources. It's LiDAR, radar, and an optical. And ideally, this is the perfect elevation data set. It's based on LiDAR, it's a laser, it will penetrate canopy, and it's small enough that it will measure in between houses. So you're really measuring the terrain. And you can create beautiful elevation models with it, resolution of, let's say, 1 meter or even 1/2 meter. And this is what you call a digital terrain model, a DTM. So not just the digital elevation model, DEM, this is DTM. And this is a picture. I didn't put a scale here, but this is in Austria. This has a camping ground in it, and I climb these mountains, and my girlfriend flies off these mountains with her wing. And I've been hiking here loads. And you can see beautiful patterns. You can see a very nice ridge here, a very steep ridge as well. So if you can have a data set like this, local, based on LiDAR, fantastic. You're golden, you're in business, you can do basically anything you want. Of course, that's not always the case. So for the same area, this will be the global elevation model. And you see it's 30 meters, so it's a huge jump in resolution. Suddenly everything becomes pixelated. It's based on radar. I will not tell you which source this specifically is, but this is globally available. But you can see the nice, very sharp ridge, it's gone, right? Definition gone. And most importantly, if it's a global elevation model, it's probably radar or optical based. It will be a digital surface model. It will not have measured the terrain, it has measured terrain and canopy and buildings. There's some sort of bias in there. And you can see that here in these circles. If you compare it to the DTM, you see it's actually nice and flat in this valley. And if you then go to this global one, you see suddenly a forest popping up, and you see some urban signal. So global elevation models, they're a surface model, and they have positive biases where you have houses and vegetation. So this is very important to keep in mind, because of course, if you want to do flood modeling, let's say, it will look like that small city there, that village, is not flooded because it's so high in the global elevation model. But that's because it's actually measuring the top of the houses. They will not flood, but street level will definitely be flooded. So that's a big thing to keep in your mind. Yeah?
What do you mean by global versus local?
So this LiDAR, local, I call this local because if you have LiDAR, this is a raster data set based on a LiDAR collection from often an airborne platform. So you fly an airplane with a big laser installation underneath it. And because it's an airplane, the range that you're collecting is limited. So you cannot take an airplane and fly around the world and measure it like this. So this is quite expensive to do. Also because that plane has to fly in certain patterns to actually fill all of this up to a certain density. So local LiDAR data sets are expensive. As I will come to the next slide, that's why availability of LiDAR data sets, well, all over the world. You can see basically this is a picture from Open Topography. Great website, great initiative. They collect open LiDAR data sets that you can download and use. And they do so for the US. It's a US funded initiative. So the US is nicely covered, United States. New Zealand is also covered because New Zealand was collecting data and thought, well, this is a lot of data to store. Let's call Open Topography, and they host it for them, paid of course. And then you see small dots across the globe, but those are mostly, let's say, research data sets. That's an earthquake, and then they do a local LiDAR collection, or there's a single volcano that they want to measure because it's active. So there are no national data sets outside of that, except for Europe. I put some pink dots on the map myself here, and that's because Europe has some national LiDAR data sets. Like the one I showed you for Austria. The Netherlands, where I come from, has a very, well, the 5th iteration of the local LiDAR elevation model. But I'd say good national data sets, they're completely limited, and there are none in the global south. And this is a problem because where we are in the Netherlands especially, we're pretty well defended against sea level rise and storms and such, but all these other countries, especially in Southeast Asia, they'll be hit by subsidence, by sea level rise, and we don't actually know the elevation. We just don't know. We have global elevation data sets, but they have their issues. So I want to talk a little bit about global elevation models and how they have progressed, but first I will answer the question of Milan. Yeah?
I just have one conceptual question. So with this example that you gave, you said like, hey, this one area there's actually some forests, some trees.
Yeah.
I understand that for flooding purposes, you don't want to assume that the elevation is higher there because the trees obviously like not that wide. But once you have a building, let's say you have a really big building, would you kind of want this data set to not include the building, even though from a flooding perspective, let's say the building is really well sealed, so it couldn't actually flood, so you would have actually more water going through the streets because, well, that's the only space where the water can go. And so technically you would want to include your elevation data set, the building. Like, where do you draw the line?
You're right. The distinction between DSM and DTM is, well, there's a gray area in between, and it depends on the purpose of your analysis. And indeed, for flooding analysis, you often, well, you want to have a very high resolution data set that you can indeed measure in between buildings. And urban flood models will indeed take most buildings, bigger buildings, as non-flooded or non-floodable. So you have more forcing through the streets, which is indeed the big danger when you have major floods in cities. It will rush through streets and surprise you. So good point. It depends on the analysis. I think my main point is here that if you have a global elevation model, and we'll look at some more examples, it will be the surface. And it's a low resolution, so you cannot actually see the streets. So this is a diagram from a terrain book published by my research group. It's an open book used in teaching. It has nice details about, well, all sorts of elevation modeling. But what I want to show here is that there are essentially four major global elevation models: AzoresTV, Aster, Tandemix, and ALOS. And there are some new ones upcoming, but from these four base models, let's say, based on radar and optical, there are derivations and new acronyms, because this whole world is all based on acronyms. So there's NASA DEM, there's World DEM, which became Copernicus DEM, and then very importantly, all these base data sets, especially because they are mostly open, there are derived data sets that try to correct for the biases present in them. So all these global ones, they have some errors, they have the bias of the buildings and vegetation. So people try to correct that and arrive at some sort of a terrain model. Yeah. Every dam will provide a water mask file next to it. So you have a tile which contains elevation, integer or floating point, and there is often a mask file, maybe only int8, that provides probably at least land sea in terms of pixels, and if you're lucky, also the river pixels and lake pixels. And of course, this can only be done to a certain extent. It's discretized, so the river is basically pixels shifting, and eventually rivers become so small or lakes become so small that they're not registered like that. And the sources, they can be from other missions, it can be done on the instrument itself, because radar will behave, well, not very well on water surfaces in these modes. And there will still be errors on the edges of these land-sea boundaries. Yes? All these dams go down do not go down to the floor. They stop at the land-sea boundary. And the rest of the data is none. So it's really only land. Bathymetry is a whole different topic altogether and cannot be measured in one go as we can measure the terrain, sadly. Still no bathymetry, so they stop at the edge of the lake. Just because that's the signal you've measured. With radar and optical, you cannot penetrate the water body to measure underneath. It would be very cool and useful if we could, but we can't, sadly. And in terms of, it's always difficult, because as soon as you got water in part of your pixel, I mean, if a pixel is 30 by 30 meters and is partially inundated, you get weird signals. So depending on the dam, depending on the process or the base resolution, some filtering will take place, or it will be detected as water or not. And if it's not, there might be an error in there. You can also imagine that because you have tides, and the tides can be rather large, it depends mostly on when the radar image was taken, whether you have a low tide or high tide. So your land sea boundary might shift or do weird things. It's complicated. I think basically the whole point is, from the whole lecture, maybe be careful with global elevation models. I mean, they're fantastic, but yeah, caveats. Anyway, back to the presentation. Diagrams are a bit boring, right? So let's take a look at actual pictures. So I've taken, this is Florida, South Florida. There's Miami here, Everglades. And this is AzoresTV. It's a JPL mission from the top of my head. It was the first global elevation model. I can bash it a bit here, but I want to stress this was the first global elevation model, 2000, 2001. Before that, we had no clue. We just didn't know. There were basically, you used leveling, and from a certain moment in time, you started using pictures from aeroplanes and trying to do some photogrammetry or manual stereo methods. But we had no idea about global topography as a whole. We basically isolated point measurements, that was it. So AzoresTV, basically, we entered a whole new era of remote sensing, where we could use elevation to do global terrain analysis. So this is huge. There have been many versions, and this picture is actually NASA DEM, which is a AzoresTV version 3 corrected with ISAT. And you can still see all kinds of interesting things here. Basically, everything that's red, higher than 10 meters here, is some form of building or vegetation. It's definitely not a terrain. You can also see that there's some diagonal striping in here, especially in the northern part, and that's purely radar artifacts. And even the third version with bias processing from ISAT was not able to fully remove these artifacts. The uncertainty in the measurement is also so low that the elevation is stored in discrete numbers, so as integers. So just 0 meters, 1 meters, no centimeters involved, whole meters. And it's referenced to the EGM 96 geoid. Moving on, now we got to Aster, which is the first optical elevation model. So that's not INSAR, that's well, basically photogrammetry from stereo imagery. This is a collaboration between Japan and the US, so METI and NASA. And also integers, they're striping, but I'm actually not sure what I'm looking at. It's all red, and I don't see really patterns between vegetation or urban areas or anything at all. So this is a good estimate, but the error margin is probably around 10 meters at least here in this data set. Then we go to ALOS, which is another optical one, and again, suddenly you see more patterns here, right? You again see urban area and a lot of vegetation, and you can actually see some dikes or levees, again, in the data set. You'll also see a sort of circular artifact in the processing, which is probably some overlap in stereo stereo imagery. And we also see that there is now, because this is based on optical pictures, and you can keep taking optical pictures and do reprocessing and keep reprocessing. So there's even a 5-meter version of this data set available commercially. So you can buy, this is the freely available one, 90 meters, maybe 30 meters, but you can go to 5 meters if you pay for it. Let me check that. I thought there were 2 optical and 2 radar, but it's optical, right? Okay, cool. Whew. Then I don't have to correct the book. That saves. And then the latest, and I'd also say the greatest, just also because it's the latest, is Tandemix. That's the German Space Institute, collaboration with ESA, Airbus. And via Tandemix became Copernicus Dam, which Anshu already talked about. This is a 30-meter global elevation model, and it's beautiful. And that's what everyone is using now, because it's the latest and the best. So this became Copernicus Dam because ESA bought it from Airbus, and Airbus processed Tandemix into World Dam, which they sell commercially. And basically, well, depending on where you're from, your taxpayer money, your tax, actually paid for this data set. So you can thank yourself also a little bit for this data set if you're from Europe. And this is also the first one, I believe, with floating point numbers. So suddenly we're talking about, well, centimeters or something like that. Reference to EGM 2008. And there's actually newer versions being made for Tandemix, so, and newer versions of World Dam. I'm not sure if we can get a new version of Copernicus Dam from that. And of course, there are commercial versions of this as well. But the amount of detail in here is incredible compared to all the previous ones. Because AzoresTV was originally a 90-meter data set, and it has been reprocessed to 30 meters, but it's sort of, well, you can say it's faked in a way, right? There's some information there. Don't want to be too harsh, right? AzoresTV is the first global elevation model, but Tandemix was essentially collected at 10 meters and then resampled to 30 meters. And you can still see that detail, even in the 30-meter version. And you can see small individual levee roads, also in the Netherlands and in other polders in the world. And it's a beautiful data set to look at. That said, still, vegetation, urban areas, all in there. Yeah. All global elevation models, including this one, include vegetation and buildings. So everything that's basically orange and red is urban or vegetation here. I think only the blue parts are actual terrain measurements in this one. Sorry? If you have a mountain and there's forest on top of that, so then you have a huge altitude and there's maybe an offset of 10 meters of bias in there.
Is Florida so flat that the red parts are just urban areas like they're from mountains?
No, it's basically, this is very flat. This is also because my research concerns most of the low economic coastal zone, so let's say 0 to 10 meters. And that's also the area of interest if you want to look at coastal flooding and sea level rise. So what you see is the land is actually what is more marshland, I think, for most of this. And that's really low. That's just a meter above sea level. And everything that's red on the left-hand side, that's indeed vegetation. That's just trees. And you're measuring somewhere in the upper part of that canopy. So the reason I have not finished my PhD yet is because I'm just scrolling through this data set, looking at new patterns that I don't understand yet. And yeah, it's a lovely distraction to have. Okay, but seeing all those trees and urban settings, many people have said, look, we need to correct that. We need to remove that positive bias so we can do actual terrain analysis. So we can take secondary data sets, maybe some lighter data sets. We can do machine learning. We can do some regression methods. We have some optical data sets where we can basically take a land cover map, whatever the source, and say everywhere there's trees, we should lower it a bit. And Merit, multi-hour improved terrain from the top of my head, lovely acronym, did that for AzoresTV, one of the earlier AzoresTV versions. So it's a global correction for vegetation, and this is the same area. And as you can see, especially here on the southwest part, a lot of the red has been removed. Not all of it, so this is a good improvement. But you also see that in Miami, everything is still red. So it did not remove buildings. Also did not meant to. It was really for vegetation. And it tried to remove errors, radar, artifacts present in AzoresTV. So there's way less striping also in Merit, so that's good. But you can also see a huge diagonal stripe that's not actually terrain, but it's still a radar artifact that could not be corrected. And this is actually a share-alike license, so you can use this freely. New in all these slides, on the left side, I put a picture of Amsterdam in there, just to give you an indication of what a city looks like. And Amsterdam does not have too much high-rise buildings, but essentially it should be pretty flat there. It should be all green in Amsterdam. So it's a more zoomed-in version than the whole of Florida, essentially, or southern part of Florida. So this was Merit. I think we're still using this in the towers. Yeah. The black parts in that picture is water. No, you should see it as excluded. And yeah, it's a bit bad because this turbo color map also becomes black at 0. It's related to the question about the water mask. It depends a bit on your data set, but often water will just be 0, like C will be 0. Which is weird because it isn't, but you really have to use a water mask to basically remove those values. And some data sets will put 0 for all water sources. Copernicus then has done some corrections. So World then probably has done that, where they do some stepping. So C is 0, and then rivers are incremented in ½ a meter. So some lakes are 2, and then becomes 2.5 in the river. Just so the water sort of could flow downhill, which is good. It's a sort of hydrologically conditioning, but you still need to use the water mask. Otherwise, you don't know which values actually land and sort of faked water surface. So this is Merit, and this is a popular research topic. So this is Coastal Dam. They used ISAT2 for training and also local LiDAR validation datasets. It's a commercial version only for the, well, I think up to 120 meters above sea level. So it's a coastal elevation model. It's global, but only limited to the coastal areas. And there are many of these. And as you can see, almost everything is blue, which is more correct than everything red. I'd say this one is still slightly too low, but it's a very good improvement. And this is what they're also using. This is from the people at Climate Central from the top of my head. And it's a commercial data set. So most of these data sets are free for research purposes, but as soon as you use it in a commercial setting, you have to pay for it. So this is Coastal Dam, then there's FATDAM. So Coastal Dam is an easy acronym, right? It's Coastal Elevation Model. FATDAM, nice acronym, is Forests and Buildings Removed Dam. So this is a global one, also trained with local LiDAR datasets and ISAT2 globally. It's also a commercial one. And this has, well, slightly different patterns. Where sorry? These are levees, I believe, with some vegetation. If you would zoom in, you could see major highways, especially in Miami. But I can see the individual pixels here. That's way too big for highways. Okay, cool. Yeah, if it's a highway in basically flat terrain otherwise, it's definitely visible. If it's a highway in an urban setting, it becomes quite hard. But then it's more like a valley, actually. That said, this looks slightly worse than Coastal Dam, right, in terms of vegetation filtering. So all of these data sets have their own biases and trade-offs. Then recently, Diluvium Dam came out. Diluvium Dam is a Latin term. And this is actually looking really good. Machine learning based. The only big drawback is that this used individual pixel regression in the machine learning framework. So on average, the bias is 0 almost. It's like one pixel is 2 meters too high, and the pixel next to it is 2 meters too low. So on average, it's great, but it's an incredibly rough data set in terms of roughness in pixel differences. So if you smooth that, I think it would already be pretty much perfect. The asterisk here is that there is a local LiDAR data set for Florida, and I believe they trained with it, and that's probably why it's so good. And this is a non-commercial one. So this one surprised me. This is released beginning of last year. Yeah.
What are they regressing on?
Well, for the details, you should take a look at the paper. But basically, all of the previous ones, they take Copernicus DEM. Even Coastal DEM originally was trained on AzoresTV, but in the latest version, which I did not show here because I haven't downloaded it yet, they all train now on Copernicus DEM. They use ISA2 for basically regression, and then they put in as much data sets as possible. Just as much features as possible. So that's, some do only a single land cover map, some basically take all global land cover maps. Night lights, stuff like that for urban areas, population density data sets. I'm not sure if any of them is using OpenStreetMap, but something like that. And these all correlate to some extent, right? They also use some tree height data sets, which are actually derived from ISA2 and JEDI, and it's just mixed, and it works, so I get it. Moving on, this is Diluvium DEM, and then very similar to this, and this is not a corrected DEM. This is just taking ISA2 LiDAR data, global LiDAR data from a satellite that's very sparse, and then you can make an actual DTM purely based on ISA2 measurements. The only drawback is it's a 1 kilometer resolution. So not 30 meter like the previous ones, but if you're not interested in zooming in, but like a global overview, this actually works. And this is really close to the actual terrain. It's only very coarse resolution, with the exception of a few outliers. You can see them there, almost black pixel. So this requires good outlier filtering, maybe better than this. I think in a recent paper, I showed that you could go to a 500 meter global resolution nowadays, just because there's more and more satellite LiDAR data available. So all of this, because I said this is my research topic essentially, I made my own attempt at this. This is called Delta DTM, the latest in this row of corrected elevation models. And it looks quite similar to the ISA2 one. At the moment I published it, I think it was pretty good for the coastal areas. That said, I can easily point out my own faults in this, and you can see very nicely ISA2 outliers and stripes right here that I didn't filter out correctly. So I have my own type of artifacts in terms of data sets. And this is also non-commercial. That said, let's look at the actual terrain model. And this is based on LiDAR. And this is the NOAA coastal sea level rise data set. And this is the actual elevation. And you see that orange only happens in the top part, and the rest is deep dark blue. And you can also nicely suddenly see the morphological details of some, I believe, almost sand dunes along the coast. And maybe also interesting, looking back at Amsterdam, Amsterdam is basically a green blob, but with highways around it. There's a ring of highways. And if you go back in all these data sets, that's completely invisible, right? It's in none of these corrected data sets. You can see that infrastructure detail. So be aware of that if you use global elevation models. Now, my last word of warning about global elevation models, and especially the corrected DEMs. They're great, just like AzoresTV was the first one, and it's great to use, and finally you can do global analyses, but you still have large errors. So, for example, we measure sea level rise in millimeters, and if you go to sea level rise scenarios, you're talking about maybe a meter in 100 years, depending on the scenarios, depending on the location. But let's say you take a delta DTM, which has an error average of, let's say, a root mean square error of 0.75 centimeters. If you now would bin the world, make a raster, discretize it into, let's say, a bin of 0 to 1 meters and a bin of 1 to 2 meters, basically classify the world like that. Even with an error of 0.75 meters, you would have a confidence of around 50%. So only half of your binning would actually be correct. The other half would be in a bin next to it. So it's actually very hard to do sea level rise analysis with any global elevation model, or you have to at least to be aware of the uncertainties involved here. Also, recently, Guth and others had a very nice research paper that they showed that all these corrected elevation models, they're great in the sense that they're really reducing the error in terms of the urban setting and the vegetation. They're all removing it pretty well nowadays. But if you look at derived metrics, like the slope of the terrain or the aspect, so the direction in which the slope is pointing in, they're actually doing worse than the original input data set, essentially because it has not been trained or optimized for that matter. So, enough words of warnings. Let's actually go to, I think, Julia. Yeah, Julia. We have the geomorphometry package, and you can take any abstract array and you can calculate aspect, slope, curvature, relative metrics. You can do hydrology with it, like depression filling of elevation models, stream flow analysis, so looking at how the water flows, visualization, because actually the pictures I showed you, just a heat map of elevation is often not that interesting in terms of details, and also filtering of terrains, morphological filters. And these are all available in the package geomorphometry, and you can even choose between different algorithms in terms of slope and curvature. That said, there are some caveats that I want to go into, but first let's look at some details. So if you visualize that, slope and aspect, this is what you can do in Julia nowadays. If you're into terrain analysis and choosing a nice color map, so that's slope, aspect, and curvature, you can do visualization. So this is also what you can do in QGIS or GRASS, but you can now also do in Julia. So there's hill shading, multi-hill shading with different light sources, and a personal favorite, PSSM, where you actually don't use light sources, but actually take the slope as a sort of input and visualize that. So I think the contrast is highest in the right-hand side picture. And this also shows a lot of details of the actual data set. You can actually see the triangulation of the terrain right in this part here, the terrain artifact. Yeah.
Could you explain, I didn't catch the difference of generating the most right versus the most left.
So the left one is hill shading, which is basically saying there is a single light source, like the sun, on the terrain, and then calculating basically what you get back, or akin to that assumption. Yeah? Okay, let's first finish this one then. And the one in the middle is taking multiple light sources from all directions. That's why it's lighter in less dark areas. So that's all based on the elevation and basically an angle. And the right-hand side basically looks like the slope one this is the left-hand side, that slope. And this visualizes slope, but has an extra weighing factor for steeper slopes that becomes darker. And this is more how you would interpret terrain if you would actually print it or make a 3D thing out of it and put it in front of you. So this is more meant for visual recognition, human visual recognition.
Is there any kind of post-processing technique that will allow you to take any of the left-hand images and generate the right-hand side without going through the process of a more sophisticated functionality?
Well, these are very easy and quick analyses. This is just having opening a thing like with rasters, for example, and just calling PSSM, and you have that within, well, I don't know, sub-seconds, milliseconds. So you can do any of this, and you can make your own changes to it. And of course, the algorithm will give you just a raster back with new values, and you choose essentially the color range and the color scheme to visualize this. So that's up to you, and you can do very fancy things. What you often see in very nice, beautiful maps is that you combine aspect or with a slope map, and then you have beautiful, becomes more like art, right? How to make a nice topographic map. Anyway, the other question.
Could you go back to the previous slide? Well, it's also related to this one, but could you do it for any topographical, a way of topography? So if you have, say, from here up high, you download the topography, could you do this kind of similar analysis on that as well?
This takes any abstract array. So, sure, what it actually means to do slope analysis on a precipitation intensity map, I have no clue.
No, as in a sense, this would be useful. I was thinking that this would be very useful if you are talking about coastal offshore propagation and using the aspect and the curvature to determine, say, what direction offshore and then you would do the Hong diagrams.
Absolutely, yeah, sure. Yeah, you can do some hydrology analysis. So there's depression filling, stream flow. So this is basically if you say on each raster cell you drop 1 unit of water, where does all the water end up and in which direction? So direction is on the left-hand side, and the combined accumulation of those flows on the right-hand side using, I think this is the infinite. Anyway, that's a specific method. But all these methods use basically a map window operation of a stencil by 3x3 window, just taking a single cell and all of its 8 neighbors, and then determining directions or slope. And that's how it's been done since the 80s. And there are improvements on the way, which I want to talk about, because using that window has some implications. So I said I've implemented curvature, and sure, I found curvature definition on one website, but here's this nice paper by Minar, who took a look at all the curvature definitions. So this is like a single definition, like slope or aspect, and he found like all these mathematical definitions for curvature, which is a complete pain in the ass, because I don't know which one I want to implement, and it means that depending on whether you want to use Grass or QGIS, Julia or Python or other specific Python package, your answers for curvature will be wildly different. And this is not only the mathematical approach, so this could be the stencil and which neighbors to take into account to basically calculate secondary derivatives, but it could also be that Esri, for example, they say, yeah, curvatures, they're so small, we scale them with a factor 100 or 200, just so they become a nice visualization or a range of numbers that you can interpret. And some say, let's say that curvature like this is always positive and this is negative, changing the mathematical definitions for, well, human perception. So I'm trying to figure this out in the package and giving the user a bit of a help in what algorithm to choose and what it means. But this is like a rabbit hole that I'm diving into now. And likewise, and this is a fun one. Like I said, this is all map window operation and then looking at the neighbors, right? So there are offsets from a central cell. So a very easy question to you, no maths involved. Giving the offsets of this stencil, so you do map window operation with this stencil, you have these offsets. For these offsets, which one is northeast? If you are operating on an array in Julia, which direction is northeast?
I'm not following. I'm going to give you an answer so we can.
No, I think any answer is basically correct, or some package somewhere in a language has implemented like you think it is. But it's a bit undefined. Because essentially, it depends on your column row order. That's one, and Julia is different in that compared to Python and other languages. So that's basically already one axis. It's normal for images to basically display positive axis, the horizontal axis is positive, but for the vertical one you go down, right? If you display, if you create an array in Julia, in the replicator it's displayed like this. It goes down. So that's also why the stencil goes positive downwards, but that's already a choice. So for me, I thought northeast is actually the lower left cell, because you go down and that's sort of positive. Anyway, I'm figuring out a good way that you can change this on the fly if you want to, but again, this will majorly influence all answers like aspect compared to other packages. And that can really be a pain. This is just about definitions without thinking about actual coordinate axes of your projection and any of that other stuff. That said, I'm now using stencils. I want to shout out to Rafael for creating this nice package. I first started using, I think, image filtering in Julia, which has map window. That was incredibly slow, so in an issue there was a new proposal for map window that was way faster. I used that. Then I moved to local filters, another great package, but it produced horrible code, well, not readable code. It was way faster, but not really readable. And now I'm changing to stencils. And this is an example of stencils. Basically, you can, instead of just always taking a 3x3 window, you can very nicely define, for example, I made these pull requests on stencils. You can now have a circular window with a hole in it. So you can basically do a ring-wise window operation, and you can define the window sizes. So on the left-hand side, you have annulus 2:1, and that's basically width 2 for the outer circle and 1 for the inner circle. But you can also say 5:2, and then you have a way bigger or thicker ring. And then there's also wind direction, so you can do ordinal, and then you have the cells on the left-hand side. And if you do 1, that's your normal 3x3 window, and then the edge cases. But if you do window size 3, they grow, and you can even name them. So with a named stencil on the bottom, you can actually give wind directions to these offsets. And you can access these wind directions in stencils when you do the map window operation, and that makes it very easy to make readable implementations of all these algorithms I discussed. Because if you want to do slope, that's basically west plus east divided by 2, and looking at those relationships. So the code becomes very readable. So this is great, and this is work in progress. So I hope to publish this somewhere soon, next breaking release of geomorphometry, with a nice new documentation using VITEC. So there are multi-sized windows based on stencils. There will be weird windows like the annulus one, but also slope in 1D. And the major one is support for geographical rasters. Because if you operate on a stencil 3x3, you basically assume everything has the same distance. But if you have a geographical rasters, like most elevation models, the distance from in your x direction is not the same as the y direction, and you need to scale them correctly. So that's upcoming in geomorphometry. And I will work on it this week. I'm not promising it will be finished this week, because there's always new, fun, interesting discussions and bug fixes to do. Yeah, that's it. Any questions? So you're asking from distance from coastline? You're asking for distance from coastline? Yeah. There are functions like that in geomorphometry, and their improvement. It's nice to actually see the improvements also in terms of the science from the 80s to now. The distance from coastline, especially given slope or other indicators, those are cost friction maps. It's a whole domain on its own, and you can calculate basically the shortest distance to the coastline given a sort of cost operator, and that can be slope, can be something else. And I believe Rafael is also using that in basically species distribution, right? Because species want to migrate, and They will not cross the mountain, but they will go around it, and all these kinds of things.
So is a functionality already available?
It's already in the package, and there are large improvements on the way because science have made nice improvements. There's now the package iconal, which uses these nice equations and makes it way faster to calculate these cost-distance maps. But cost-distance is essentially what you're looking at. Any other takers? Well, then I believe it's perfectly 12 and time for lunch.
Thank you so much for the presentation. We will have our lunch break until 1 p.m. For everyone watching online, we'll be back in 1 hour. Thank you.